So hello everyone, welcome to our session on profiling a serverless host with vHive. My name is Lazar Cvetković. I'm a PhD student at ETH Zurich in group of Professor Ana Klimović. So we are going here to talk about implications of serverless on computer architecture. And let's first say that serverless workload has some kind of unique characteristics. And there have been a lot of work on trying to figure out what are the workload characteristics of serverless. So for example, I would like to mention a paper called Serverless in the Wild, which says that plenty of functions are invoked less than once per minute, and that most serverless functions have a quite short execution time. We are here talking about 60 millisecond mean time. And one also thing is that there is extreme multi-tenancy, which means that over 100 to even 1,000 of function instances reside on one physical CPU. And that's what we are interested in. So our tutorial here aims to study a single serverless host using vHive, and we are going to show you live how to analyze architectural implications of multi-tenancy. So first, let's go to some theory and how performance measurements are done on CPUs. So CPUs expose some metrics, and concretely here we are talking about performance counting registers. So for example, one register can be number of cache hits, number of cache misses, and so on and so forth. So I think that Intel Haswell architecture has something around 219 performance counters, and you really need to be an expert in order to analyze their semantics and what information they can give you. Some of them are not backwards, they don't have backwards compatibility, and some of these metrics can be misleading. So you really need to be an expert in order to understand what's underneath, and you really need to know the details of the microarchitecture. Okay, so for that reason, in order to bring this to high level, Intel developed something called top-down methodology that was done back in 2014. And we are going to use this methodology and these tools in order to classify bottlenecks and figure out what should we do in order to improve performance of our server, individual server. Okay, so let's see how it looks like. This is a top-down in a nutshell, but we first should say that CPU is often divided into two parts, front end and back end. And front end, in this case, is responsible for instruction fetching and instruction decoding, whereas back end is so takes care of instruction scheduling, execution, and eventual retiring of instructions. So we are here talking about out-of-order CPUs, and modern CPUs can issue four microoperations per clock cycle, and they can retire the same number of microoperations. I think that even with the newer architectures, this number rises to 5, but never mind. And the goal of CPU is to populate all those 4 slots inside each clock cycle. And what should we do here? So we want to classify bottlenecks, and we do that by counting whether we have empty slots or we don't have them. And for each slot, we ask ourselves in each clock cycle whether it gets a microoperation or not. So if it gets a microoperation and that microoperation eventually retires, then we put it into retiring category. If it gets a microoperation, I'm talking about slot, and it doesn't eventually retires, then we are talking about bad speculation category. If the slot remains empty, then we can distinguish between front-end and back-end bound overheads. And let's see how it looks like. So when you run, when you profile application, you get some numbers like this. These are some measurements we got. And you have these 4 categories. And then, for example, you get 56.7% for back-end bound. And then you ask yourself, how can I improve my program? Because this doesn't tell me too much. I want to figure out what is the concrete problem. So you go one level deeper, and this is the level 2 categories. And then you run the PMU tool, and you get number like this, for example. And then you go to level 3, level 4, and so on. So what this tells us, there are these few of these categories, and I would like to tell you like about few of them. So here we have fetch latency, which means that which tells you if you have high percentage there that there is some overhead in instruction fetching. Fetch bandwidth means that there is some overhead in instruction decoding. Then if we talk about bad speculation, we can have either bad branch prediction, which is the so it means that branch predictor is not performing well, or we can have bad data speculation. In both cases, the instruction will not be retired, right? Retiring is a category where we eventually would like all our instructions to end up. And finally, we have core bound and memory bound. Core bound means that execution units, so functional units inside backend of CPU are used suboptimally. So that means that some of them are not filled in every clock cycle or so. And there are a few more reasons why your microoperation may end up in this category. Or you have memory bound, and here we talk about some problems, some overhead in memory subsystem. Okay, so the list, what you see here on the screen is not exhaustive, and there are plenty of these categories. Each of them have different semantics. And in order to, so when you get a number like this, 22.86, you open a manual, you see where the problems may be, and then you try to like improve your code. And so in Intel manual, there are cures like explicitly written what you can do in order to fix some of these issues. Okay. And sorry, do you have any questions on this topic? Okay, also no. So we have here our tool, and this is its architecture. So let's talk about measuring methodology for a bit. We do measurements in three phases as usual. So we are talking about warm up, profiling, and cool down phase. We are interested here when the system is in stable state. So that means we need to warm it up, implying that we don't want to count cold starts, and we won't discard such measurements, sorry. So we take only measurements from the profiling phase. For that, we have here you see these gray boxes. Up you have socket 0 and you have socket 1. So we have a vHive worker residing on socket 1 that has a certain number of firecracker instances that run there, and we put a load client and latency client on other socket because we want our measurements not to be biased. What that means is that if you want to generate a stressful multi-tenant environment, load client will do that, but it will use a certain portion of CPU. Therefore, your measurements may be biased in case you put them on the same socket. On the other hand, you have latency client, which measures latency, and that's the results you will read. How it works is that you have a request issued to a firecracker instance, or and then you get a response, and you cannot issue further requests until you get a response. And it's the way how it works. So we call that closed loop system, and we have load client, which is an open loop. So it models that you have unlimited number of clients and that you can have like almost unlimited number of requests there. Whereas with closed loop, you have a fixed number of requests in the system. Supported modes here is I'm talking about measurement modes, single configuration mode and multi-tenancy evaluation mode. So the former, the idea is to have a fixed number of VMs and to sweep requests per second. So you are increasing the load until you reach maximum that you want to reach, or until 19% tail latency is 10 times greater than unloaded latency. So that's a criterion when our experiment stops. The other mode is to figure out what happens if you change the number of VMs on a single host, and it's the same as in single configuration. So it means that you sweep the number of requests, but you sweep number of VMs as well. So you start with, for example, 1 VM, then you go through all the RPSs, then 2 VMs, and so on and so forth. So that's how it works. Okay. So I'm going to give you a live demo how you can use these tools. So let me show you. Okay. You cannot do this currently because Google Cloud Platform doesn't allow you to have a look into performance registers. So I will be using Cloud Lab machines which give us access to these hardware things. The reason for this is GCP probably doesn't allow it because of security. Okay. So I'm going to clone this particular branch I have prepared of the vHive repository. And I'm going to set up the tool, which is quite simple. You're going to see. Yeah. So you can find in all the instructions on this hyperlink, and yeah, the slides will be posted. So you'll have access to all these things if you want to try this at home. And I'm going to run this now. The setup is quite simple. I'm going to skip install Git because we already have that on Cloud Lab on this type of machine. And I'm going now to run Firecracker in the background with screen. So just to make sure it's running, it is okay. Okay, so single mode measurements. I have here prepared some measurements to do. And here we are running with 2 VMs. The peak RPS we want to achieve is 4K, and we are increasing load by 25%. So starting from 1000 RPS to, so we increase by 25% of 4000. So we end up with 1000, 2000, 3, and finally 4000. So this will execute for probably something less than 2 minutes. Yeah, let me tell you, so this takes time. And in case you want to run it like with a that is more fine-grained, then it will take much more time. We are going to see some output soon. Okay, it's running, and it gives us percentage that this function hello world that I'm using on this single host is backend bound with percentage of 54.83. And then after this finishes, we are going to see whether bottleneck changes with a different number of requests per second. And after we get these measurements, we can run for level 2. So that means that we can dig what happens in backend bound, and we can therefore find the bottleneck. Okay. So you can perform measurements on every level that you saw on while I was describing them. This is for level 1. When you run this at home, if something breaks, or for example, you use ckill to stop the measurements, you need to clean the machine and then rerun everything, which won't take too much time. Like just run the install script and steps, and everything will be fine. Yeah, so I've explained what happens here. We have, for example, 4K RPS, we have 56% of micro operations end up in backend bound category. And we are going to see what happens with when we dig deeper on level 2 now. Okay. So we see that memory bound issues arise with percentage of 33.5. Also, you can change the function you run here. We are using hello world function that is like just measuring the overhead of the whole machinery behind serverless. It just enters and exits, like the function doesn't have any useful code. This is just a dummy thing to show you for purpose of demonstration. Okay, yeah, and it completed. So you see that at 4K RPS, the distribution of overhead is a bit different. So 30% of memory bound and 24% of core bound. So that means that, again, you open manual and then you see, like, this is a pointer where you should work on. Okay, this is the first mode of execution, and I'm going to go back to slides now to show you the second one when we sweep the number of virtual machines. So this is what you have seen. I put these commands on slide, and this is just the sample output. Okay, we see that the results are almost the same. Not really exactly the same number, but something like plus minus 1, 2, which is something that is expected because we are not alone on the system. And this is when we sweep the number of tenants. So we go here from 2 to 20 and conduct measurements. These are measurements on level 1. And here you can see how bottlenecks change when you change the number of VMs. So yeah, one reminder, we want as much as possible micro operations to end up in retiring. And you see here that if you increase number of VMs, front end bottleneck becomes dominant. Then you can conduct measurements on level 2 and end up with something like this. This is for front end, for example. You see the distribution here that fetch latency rises with the number of tenants. And finally, we can do measurements on level 3, which I didn't do individually, but yeah, this is something you can see. We have visualization scripts, like this is what our tool gave us. But this takes some time to execute, and this is the reason why I cannot do it here in front of you, because it's like 20-30 minutes for one graph. You see this distribution overhead here, MS switches, LCP, ITLB, and so on. So for example, MS switches means that I think some of the instructions cannot be executed in functional units, but have to be done with microcode, like a different way of execution. LCP means that you have you need more than 5 cycles to decode instruction, and these are some peculiarities of Intel CPUs. Okay. And finally, we can have here takeaways. So serverless workload has specific characteristics, and that means that it has implication on CPU architecture, and that means that we can, this brings a lot of opportunities for research in new architectures, okay? vHive supports Intel PMU tools for evaluation of performance bottlenecks. We have manuals, we have guides, we have visualization script that you can use in order to help you debug your server. And we have demonstrated the tools here in front of you. So for any questions, for any problems or whatever that you need, you can send me an email. You can find my email easily. And that would be all for this from me, from my side. Yes.
For x86, is there any plan to support ARM architecture?
Maybe Dmitrii should ask this. Sorry, should answer this question. Yeah, for now this is what we have, but yeah, but let me tell you that this methodology exists for Intel, right? So what is planned for ARM, I have no idea. I don't know what happens in the company.
So this one is basically made with top-down.
Yes. So this is Intel, right?
The tool is developed by Intel,
yes.
Top-down methodology. Yes. So I think we should forward this question to ARM directly.
Yeah. Okay.
No, I can tell you that. No, because ARM has a travel ban, so they're not allowed, because of COVID, so they're not allowed to travel. So yes, I can tell you proactively, no.
Okay.
Maybe remotely, yeah, but not in person.
So a little, so we also cannot apply this method to AMD server.
To what?
AMD, yes, AMD.
I mean, look, there's two things. There's the methodology, and then there is the actual implementation. Right? So the methodology is just the methodology. It's like you need a bunch of counters. The question is, do you have the right counters and how do you assemble them and so forth? And so I think it's totally doable in any architecture, but you have the right counters. Again, but how do you make sense of them and put them together in the right way? I don't think this exists in any other architecture.
Yeah, so we mentioned that this thing is not standardized, like the counters and so on.
Exactly, that's what I'm saying. So
and it changes from one version of architecture to another. Okay.
What do you see it will use this like for a server or
yeah for
would you envision to use this type of tools?
So for example, you want to pack as many function instances on one single server, and then you want to figure out how many you can pack or what is the problem in your code, for example. So
bottleneck identification, performance bottleneck identification.
But also, if you want to somehow optimize as a group developer your function, you cannot use this for serverless. Because I mean, you need to have you cannot take the top-down methodology of your service and straight out the server. You just pick the function. You can use different methodology as a service, so you can use that as you mentioned for
okay.
But if you want to optimize function as a developer, you cannot know that what is the like if you want to use that with serverless, full serverless stack and stuff, you can optimize it locally, right?
Mhm.
But you cannot optimize it.
Oh, you mean in the cloud, like you can use it on the cloud?
Yeah,
is that what you're saying?
Yeah, it's for the cloud. Cloud.
Yeah, so exactly. It's either local or like at the provider level. I mean, I think the difference is, I mean, okay, there may be micro-architectural differences. You know, Amazon is using this version of an input processor, you're using something else. But I think the main thing to think about is, you know, what is going to be kind of like the level of contention and so forth, right? And of course, what you'll get in the cloud is probably not the same. So,
Because like for me,
I hope so.
yeah, because if you have cloud server, you have thousands or hundreds of these different functions. I think interference there's much the effect of interference is much higher than the effect of the adding your functions which are more or less the same. Right. So if you have like different users, different functions, multiple tenants, all of them execute different code or work with different data, different runtimes and stuff. Like that interference if you have also like a between able or multi-threading or whatever. Like then it's not the same as doing locally and doing that on server side.
I would say the same thing that if you look at workloads and you have the same workload, the same function, they may go step by step. So they will stress the same resources exactly at the same time. But if you consider maybe like spreading functions and using functions, is a common philosophy that we have in Dragon. If you see like two applications, they kind of spread them around to like different servers, and then they stress like network or memory bundles in a different way, and you have a special high performance because somebody using memory bundle, somebody does their cache, like that type of cache, and somebody else is stressing unique as a type. Same thing.
Okay. Then thank you.